Yes.
All right. So we are starting a very new aspects of computational chemistry. Just like I told us last last week Thursday, that this area is novel, and no much work has really been carried out on these aspects. No much computational work has been done on these aspects. Most of the work done on nanoparticles or nanochemistry is usually wet lab, which is still limited. So we shall be looking at the basis of nanoparticles. So once more, you're all welcome to the School of Computational Chemistry and Biology. God has helped us. We have concluded everything about structure drawing, structure modeling, reactions, reaction mechanism, optimization. So we have finished those modules. We are done with that course. But now we want to look at nanoparticles. Now it may sound new to some persons, but at the same time to others it is not a virgin topic. So we'll begin by looking at what is nanotechnology. Nanotechnology is a multidisciplinary field that operates at the atomic and molecular levels. Why is multidisciplinary? Because it it covers diverse areas of science. It's not limited to one particular area. It's not limited to chemistry. It's not limited to medicine. It's not limited to biology. It's not limited to engineering. It's every area of science and technology can be incorporated into nanotech. So it is a multidisciplinary field that operates at the atomic and molecular levels. Now, it enables us to operate materials at their atomic level. It enables is a
The
field
door for her.
is a field that helps us helps scientists to study the behavior of materials at their atomic level.
No!
Please, if your mic is on, you can put it off. It helps us study materials at their atomic level. It is evolutionizing. It has actually evolutionized various areas of the industries and scientific disciplines. We will begin to hear about nano drugs. These are drugs that are more effective than the bulk drug material because they have been compressed, not really compressed, but they have been modeled to operate at the atomic level. So our industries are now beginning to imbibe the idea of this nanotechnology. Now it all involves designing, producing and applying materials and devices with dimension typically ranging from 1 to 100 nanometers. Now when we talk about nano, the word nano is a prefix and is 1 exponential minus 9, 1 raised to the power of minus 9. So any technology that operates at a particle size of 1 exponential minus 9 is what we call nanotechnology. Any technology that operates materials at that 1 exponential minus 9 is the nanotech. So those materials are called nanomaterials. Now we don't really mean that we are going to make them small, no, but we are going to make their atomic level, we are going to make the atomic size to be within that exponential minus 9. So it has a range. Their size can now be from 1 exponential minus 9 to 100 exponential minus 9. That is what we mean by from 1 to 100 nanometers. So the idea is not that we are making the size small, like we are making the appearance of the molecule to be small, or like we are trying to make ibuprofen, or we are trying to make artemether as a drug to become small. No, but the idea is we are trying to make the particulate size, the size of the atoms of that material, to become very small. That is the idea of this technology. So we don't expect us to be able to have smaller materials. The idea is not in the physical size, but on the particulate size. So this technology uses special physical, chemical, and biological properties that appear at the nanoscale to create new advances in medicine, electronics, energy, and environmental science. Now, what I mean is that by the use of nanotechnology now, we can create materials that will exhibit special physical properties. So when you make a material, when you make the particulate size of a material to be within that nano level, it means that we expect that material to have a unique physical properties. It will have a unique chemical properties and even a unique biological properties. Now, if I have a drug, let me say I have maybe let me use one of these common drugs. Maybe I have a lisinopril. Lisinopril is antihypertensive drug, or better, I have chloroquine or ampicillin. We all know ampicillin is an antibiotics. Now, if I have ampicillin, and this ampicillin is really effective in inhibiting the growth of bacteria. Now, we are now saying that if we can have a nanoparticle of ampicillin, that it will going to exhibit a unique biological properties, that ampicillin that has been modeled into a nanomaterial will exhibit unique and special properties. In fact, it will inhibit the growth of those bacteria compared to the ordinary ampicillin that we usually take. So if we can prepare a nanoparticle of aspirin, we are not saying that from this idea of nanotech that the nano aspirin will have a unique property compared to the normal bulk aspirin, because the property of a material depends on the particulate nature. If we have good chemistry knowledge, you will know that the behavior of any material is as a result of the elemental composition, the particulate nature of that material. Now, the behavior of a material now depends on the particulate size of that material. Most materials are always on the micro scale. Micro is 1 exponential minus 6. That is the most materials they operate at micro scale. Some even operate at milli scale. So you can imagine a material at micro scale particle size will be more effective than a material at milli scale particle size. It's just like let me use this for instance. Just like our thinking depends on our age. Let me bring that will help us. Our thinking depends on our age. You don't expect a child of 2 years to think like a child of 10 years. You don't expect a child of 10 years to think like a youth of 25 years. Now that means that, but all of us are all human beings. We are all human beings. But at different age, we exhibit different thinking. At different age, we exhibit different thinking. The same way it is in structures, in compounds, in materials, that at different atomic level, this material exhibits different properties. So I really want us to have a good understanding of this nanotech. That at different age, we have different thinking. The same thing applies to at different particle size, we exhibit different properties. Now, the smaller the particle size, the better the properties of those materials. So if a material is in milliscale, in -3 per -3, and we have a material that the particle size is within a microscale, that is exponential -6, we don't expect these two materials to exhibit the same properties, because their properties now depends on the level of their particulate size. So every particulate size have their attributed property. Now scientists have studied that the size of an atom is 1 exponential -10. That is approximately the size of an atom, 1 Armstrong. Now, if we can develop materials that can exhibit the property of that atom. Now, since the size of an atom is 1 exponential -10, scientists have now seen a way that if we can build materials that their particle size will be close to the size of an atom, such materials will be very effective. And that is why they came up with nanotech, because nanotech is in power -9, meanwhile the size of an atom is in power -10. So you see that the advancement of nanotech will make materials to begin to exhibit unique properties, because they are operating very close to the atomic level. So we are now looking at how can we use computational chemistry to model these nanoparticles before going to the lab. Can we build them? Because first, in nanoscience, the first stage is always to design the molecule. Before you produce the molecule, you design the molecule. Most times what we do is we try different nanomaterials in the lab, wasting our chemicals, wasting our money, trying to synthesize different nanomaterials, compare their effectiveness before we can take up the production of the one that is more effective. But now with the advance of computational chemistry, we skip that part of going to the lab to begin to synthesize nanomaterials. We will now model them, we design them with our system, design as many as possible, and then check their properties to model. We optimize them so that we can be able to know which one of these nanomaterials will be more effective. So you see why it's now important to embrace the computational aspect of nanotech materials, because the ideology is creeping into in most countries now is everywhere. Everybody are now trying to develop materials in nanoscale. In fact, very soon, if we have a material that is not operating in nanoscale, that material will just be abandoned, because FDA has approved nano drugs, and very soon, if your drug is not in the nano form, it will not be approved. The same way applies to material science and design. If your materials, if your molecules are not in a nanoscale, it will not be approved, because at that nano level they will exhibit unique and exceptional properties that you never imagined. That is the essence. So this technology uses special physical, chemical and biological properties that appear at the nano scale to create new advances in medicine, in electronics, in energy, and even in the environmental science. Now, for example, in medicine, nanotechnology has enabled the development of targeted drug delivery system. Now, there are some drugs that has multi-targets, but with the advance of nanotechnology, we can now develop drugs that only target a particular site, because we have built We have built that nanoparticle according to the targets of our choice. So that nanoparticle will move straight to the target size because it has been modeled to attack a particular receptor as a ligand. So with the help of nanotech, we can achieve what we call precision medicine. Precision medicine is currently our advocate for those in medical area. We want precision medicine. With this nanotech, we can now model particles with precision medicine, and they will have less side effects. The side effects of these nanomaterials are less. They are less. Even in electronics, we can build smaller device, smaller diodes. We can build ICs of nanomaterials, nano semiconductors, nano integrated circuits, nano resistors, nano diode, nano capacitors, and all the rest, nano transistors. We can build them. So it's not only applied in the area of medicine, it's multidisciplinary. But our idea remains using computational tools to model these nanoparticles. So I will be doing more of theoretical work so that we will get deeper knowledge, because I'm looking forward to see how all the lecturers here will begin to bring in nanotech in their research work. Maybe your final year project student, irrespective of your area, you can now give them this project work to synthesize nanoparticles, model it, and see the effectiveness. So I will take my time to actually build a good knowledge, so that by the time we begin to use our computational tools to model it, it will not be asking most questions like novice. Now, the potential applications of nanotech are vast. I've thought about this, offering opportunities to enhance material performance, energy efficiency, and environmental sustainability. As research progresses, the integration of nanotechnology into everyday products and industrial process is expected to increase, underscoring its transformative impact on society. We are all trying to say that as our research progresses, there is always a need for us to integrate nanotechnology into our everyday products. Nothing stops us from having nano foods. Yes, nano foods. We already having GMO. We already having genetically modified organisms in foods. So nothing stops us from having nano foods, nano drugs, nano books, nano cars, everything made with nano materials. That is the end point. Integrating nanotechnology into everyday products and industrial process. Maybe you are into drug production, you are into even our liquid soap. The liquid soap we use, we can use nano raw materials in making liquid soap. We can imagine how exceptional such liquid soap will be when you have nano materials used in making the liquid soap. So it will be so exceptional. So we are expected to increase our integration of nanotechnology as research increases. So please, at the end of this training, we should not just throw it away, but we should see how we can bring it in. Already I myself, I am already working on nano. I'm already deeply working on nano. And this class is a product of my intellectual on nano due to my years of experience and effort. So it is just like a giveaway package because it is still new to us. It is still new to us. Now, at nanoscale, typically defined between, well, okay, I've already explained about this, how materials we have high performance, high reactivity, high conductivity, high optical characteristics. Everything about nano is just perfect. Now, let me ask a question. Okay, before I ask my question, I want to bridge at this point and take one or two questions from you guys. Then we ask a question. So far from what I've been saying is a little bit simple, but I would like to see your response on that. Okay, so far, has anything entered your mind? Do you have a question? Maybe something just entered your mind. Can you share it?
Yeah, I have a question.
Okay, you help me to be audible so I can hear you clear.
Can you hear me?
I can hear you.
I said I have a question.
Okay.
You have been telling us about this nanoparticle and how it can be integrated in so many disciplines.
Yeah. Yeah, go ahead. Hello.
You see, are there any other property?
Okay, sorry, I didn't really get the question. My network trip off. Can you repeat again? Sorry.
I'm asking of properties of nanoparticle. From what you said, you mentioned one, which is a particular size of 1 raised to power minus 9.
Okay.
So I'm asking if there.
All right.
Is there any other property aside that one that would
Okay.
be used to add?
The question is outside this 1 to 100 nanoscale. Is there any other properties? There are
Yes.
so many properties of nanoparticles now, but then we are going to look at what actually defines a nanoparticle, what actually makes a material nano. There's only one attribute that defines a material to be nano. Irrespective of the nature of the material, once the particulate size of that material is within 1 to 100 nanometer, that material is automatically a nano material. So that particulate size of 1 to 100 is the ultimate definition of a nanoparticle. Then, once the material is now at this nanoscale, it begins to exhibit other particles that are peculiar to that nano level. Particulars such properties like high conductivity, high chemical reactivity, high optical characteristics, high strength, high metallic character, high binding interaction. So all these properties are now associated to the nanoscale. They are properties that are equivalent to nanoscale. So the idea is, what defines a nanoparticle is the ability to be reduced to that nano level. So once you are at the nano level, you now exhibit other properties. Now, note that you cannot exhibit this high melting point, high chemical reactivity, electrical conductivity, high binding interactions, high target delivery, high corrosion inhibition, high absorption. Not that you cannot have these properties without being at nano level. Even when you are not at the nano level, you can still exhibit these properties, but not as compared to a material that is at the nano level. So in summary, the only property that defines a nanoparticle is that particle being at the nano scale of 1:100 nanometers. Then at this stage now, that property will now begin to exhibit the same properties of that material, but now in a unique form, in an exceptional manner. That is the whole idea.
But I want to get it straight.
Okay.
I heard what you said. I understood what you said. I want to get it straight. When we are talking about this nanoparticle,
Yeah.
are we actually talking about reducing the surface area of a material to, make it more smaller, to increase reactivity, like you said, because we all know that increase in surface area increases rate of chemical reaction and all of that. So is it actually the idea, or to reduce the size, like to compress? I
Okay.
want to know whether it is about compression
Okay.
or heating.
I
Get this straight.
Yes, I got the question. Let me modify the question. Let's say the question is on this angle. I have a compound. I have a material that is big. This material is the size. In fact, physically, this material is big. Now, is nanoscience telling us that after preparing a nanoparticle of the material, are we expecting the material to become small? No. The same physical appearance remains the same. We are not expecting a big material to become small after making it a nanomaterial. No. But what are we after? We are after the size of the atoms, the size of the atoms that make up the material. So it's as if nanotechnology is focusing on the chemical composition, on the composition of that material, not the physical appearance, but in the let me come down. Let me use this example. I can make an adult to begin to reason like a child without making that adult to go back in form of a child. So if I want to make an adult to reason like a child, what I will just do is to manipulate that adult. I can even take up genetic mutation inside. I can work on the memory of that adult. Once I operate on the memory of that adult, you will see a man of 20 years, a guy of 20 years, beginning to act mentally like a child of 10 years. But this person's size still remains the same, but mentally the person is now thinking, acting like a child of 10 years. That is just what we mean by a nanoparticle. Your size remains the same, but your internal atomic makeup, the sizes of the atoms, the particulate size of the atom now becomes so smaller. The aggregates, like the aggregates of the atoms that forms that material, become so smaller, but still maintaining the nature of the material. So by the time the atomic size of that materials now becomes so smaller, we are now seeing that the materials can easily penetrate. It can easily penetrate into places where the large atomic size could not penetrate. So we are doing reduction of particulate size, not reduction of the physical appearance. Now, by the time we now reduce the particulate size, we are increasing the surface to volume ratio. We are increasing the surface mass to volume ratio, because by the time we reduce the particulate size, we are increasing the surface to volume ratio, meaning that more of the particles will appear at the surface of that material. But when the material is still at the large atomic size, there will be low surface to volume ratio. So that is all the whole idea. The whole idea is to reduce the internal particulate nature. We are not expecting a big material to become small after we have made it nano, but we are just expecting the particulate nature to become smaller. I think I correctly answered the question.
Yeah, I think you did justice to that. So, in other words, like in material science, any material that is made of nano tend to be more stronger
Good.
because the particle and then to make it to be more stronger. I think,
Yes. Yes. All right. I need more questions, because it will open it up more into deeper understanding, so that we know what we are doing. Yes. Any other question? Okay. It means we are following. let me just agree that we are following. Medukam, are you with us? Hello, Medukam.
Yes, sir.
Okay. You don't have a question? Okay. I know. As time goes on, you have questions. Okay, let me continue. Nanoparticles, which are particles within this size range, possess a high surface area to volume ratio. Okay, I've already said that. Giving them distinct physical and chemical properties. I've already explained that. Now, I said I'm going to ask a question. Let me see who will answer that question. The question is this: what will make the particle size of a material to become smaller? On what condition can we reduce the particle size of a material? We have been talking about reducing the particle size of a material from large particulate size to smaller particle size. What condition can make a molecule that has large particle size to be reduced to smaller particle size? So if I get the answers, if you really understand the question, or if you need more clarification, I will further clarify it. If you have the answers, you can also do well to contribute.
Hello, sir, please, can I repeat it?
Yes,
Can I repeat the question?
yeah. I should repeat the question.
Sure, just repeat.
Okay, the question says that we have been saying that in nanoparticle, the bulk, the large atomic size, the large particulate size, will be reduced to a smaller particulate size. Now the question is, what we make a material with large particulate size to be reduced to a smaller particulate size? That is the question. What we make a material...
Can I say?
Yeah, go ahead.
Okay, I think before now, the invention of nanotech or nanochemistry, The reason why we usually grind our samples and reduce our particle size is mainly to increase surface area.
Yes, good.
Is majorly to increase surface area and to open up more sites for bonding and for attachments to increase the activity,
Yeah,
thereby increasing catalytic effect like what you said in the first part. I think that's the original thing we already know
yeah,
before now.
yeah.
So I think nanoscience is now helping us to will I use the word to make it more official
Mm-hmm.
and to give us more aspects, more things about that thing we are grinding that
Good.
we do not know why we are really grinding it and what happens in the particular state of those substances.
Yeah. Okay. That is a very huge contribution coming from what we know to the unknown. Because you know, science is trying to bring what we know, then take us to unknown. But coming from that angle is just typical illustrations. But that we are only changing the physical nature. But like I said, nanotechnology focuses on the chemical nature, right? So I will need more contribution. Focus more on the chemical nature. Just like what he said, the nanotechnology has now opened up to another dimension, another area, other than just grinding to reduce the particle size physically. Can someone give us more insight into the spiritual, the chemistry has both physical chemistry and spiritual chemistry. So that internal part of it, the chemical aspect of the size reduction, who has a contribution from that angle?
Well, coming to the question you asked, how can a particle be made nano? I think it can be done by reducing the bond length,
Okay. Yeah.
and then maybe introducing electron cloud or shield effect. Best of my knowledge.
Okay. It is also a wonderful contribution. I like our ideas. I like our ideas, and as time progresses, we'll be doing a day will come. I will just do a breakout session where we'll share our ideas in chemistry, in medicine, and in other aspects of science, where we discuss. Okay, he said we should now look at reducing the bond length, the bond angles, the geometry, maybe including electron cloud density around the material to help reduce it. Let me just say this. Let me say this. Though I will still come back to it. I'll come back to it. The only thing that makes that particle size to be reduced is reduction. Now, reduction has to do with the gain of electrons. When electron is pushed in into a molecule, the size of that molecule tend to compress. Let me come from the angle of I want to go from what we know already, atomic properties. We did that in our year one. Atomic properties, and one of the atomic properties that we learned is atomic size or atomic radii. Now, we are told that atomic size decreases across the period and increases down the group. I pray we'll just remember that atomic size decreases across the period but increases down the group. That as we are coming down a group, that the size of the atom is increasing because we are moving from shell 1 to shell 2 to shell 3 down the group. But as we are moving across the period, we know elements in the same periods have the same number of shell. So maybe let's look at those in period 2 or sodium group, the period of sodium, period 3, whereby sodium has 3 shells, 2, 8, and 1. Now you will notice that if you go along that period where you see sodium 1 outside, the next is magnesium 3 electrons outside, the next is aluminium magnesium 2 electrons outside, aluminium 3 electrons outside. Now you notice that chemistry is now saying that as you are going across this period, that this atomic size will begin to reduce. That was where scientists got the idea of nanoparticle, that if we can push in electrons, if we can push electrons into a material, if we can pull in more electrons into a material, that the size of the material will be reduced, that the size will shrink due to the electrostatic force of interaction, that the Coulomb's force will make that size to shrink. So by the time the size has shrinked, it will not increase the surface area. So what makes a material that has a large particulate size to get reduced to a smaller size is reduction, which is the gain of electrons. So whichever kind of nanomaterial you want to prepare, just know that you are going to need an external agent that will push in electron into the other material, because one substance, most times one material doesn't really form a nanoparticle. It's usually like a complex, and most times is a complex. So when you have two materials that is complexing to form a nanoparticle, it means that one of them, which is the major agent, will be electron efficient, while the other will be electron deficient. So the one that is electron deficient is our target. We need a material that has electron donors, an agent that has electron pairs, lone pairs, so that by the time we cap them together, it will release electron into the other one that has electron deficient, that lacks electron. So by the time the electron push into that other one, it will reduce the size of the material that is highly positive. By the time we now bring in negative charge into it, it will reduce the size because we are pushing in electron. At the same time, the one that pulled out the electron, the size will also reduce. Because as electron leaves an atmosphere, it goes down to the lower shell. So by then, we begin to have materials with smaller atomic size, depending on the complexation, depending on their scale. Some of them may not meet up to the nanoscale. Some of them might even grow larger to a bulk material. But the whole idea is reduction, which is the gain of electron. So as we begin to proceed, you need to have this idea of maybe I want to produce a cancer drug. One of the most common drugs for cancer is apalutamide. Now, this apalutamide, we can say, okay, can we form a nanoparticle of apalutamide with zinc or with iron? That means what we'll do is apalutamide, we have some electron donor sites. These electron donor sites, we then reduce the free electrons. We then reduce the ion that we are using. Once the ion has been reduced, we have achieved a nanomaterial. The next thing is for you to do some characteristics, because definitely you are going to characterize your nanoparticle. If the particle size is actually within that size, you check the particle size. We have some characteristics techniques you can use to characterize these nanoparticles that you have tried to synthesize. We have TM, we have SEM, we have UV, we have FTR. Each of them we have BTS, we have ESD, we have EDS. Each of them have their implication. Each of them have their implication on the characteristics of this nanomaterial. But the whole idea is reduction. Though I will come to the principle. I will still come to the principle because it is based on three principles: reduction, capping, and stability. These three principles are what builds a nanomaterial, based on reduction, based on capping, and stability. Once you can achieve these three, you have built a nanoparticle. The next thing now is for you to start to look out for is optimal application. Where is the best place to apply this nanoparticle? We are looking at converting our waste into electricity, and that research work, we need a nanocatalyst that will speed up the biodegradation of our waste into electricity. So such kind of work, after you have built your nanoparticle, you can now begin to look out for where can I apply this nanoparticle. You can still use your computational tools to target the best application for this nanoparticle. So that is just the answer to that question. It seems I'm talking too much. I'm really explaining too much, but it's for our own good, so we have deep knowledge before we jump out and say I am a nanochemist. So a lot of institutions are currently holding seminars and workshops on nanochemistry, nanobiology, nanophysics, nanotech, nanomedicine. A lot of workshops are going on. Okay, we are on the size dependent behavior. The size, I've already explained this indirectly, that what makes the size to be smaller is high surface area to volume ratio, which increases surface reactivity and catalytic activity, and quantum effects, which is the electronic effects. So two things: the electronic effects helps to reduce the size. So once you have achieved these two things, you have achieved a nanoparticle. I think we are still within our time. So that, okay, we have 8 minutes left. Let me be fast so that in our next session we can now start touching the software. We use TeamDraw actually for that. Now quickly, classification of nanoparticles. We have different kinds of nanoparticles. They can be classified in various aspects. You can classify them based on composition, based on their origin, morphology, and function. But the most aspects I'm interested is classification based on composition. Based on composition, we have metallic nanoparticle. those who are in organic chemistry must have heard about coordination compounds, metal complexes. These are the foundational idea of nanoparticle. So based on composition, we have what we call metallic nanoparticle, which is actually my focus. My focus is on metallic nanoparticles. Examples are gold nanoparticles, silver nanoparticles, platinum nanoparticles. They are known for conductivity, plasmonic properties, and catalytic activities. So we have metal nanoparticles, either a metal with a compound or a metal with a plant material, a leaf extract, or we still call them nanoparticles. We have metal oxide nanoparticles. This is another interesting area that we'll be touching. Metal oxide nanoparticle. We must have heard about stuff like silicon oxide nanoparticle, zinc oxide, tin oxide nanoparticles. They are mostly common in photocatalysis, pigments, UV protections, and biomedical uses. So we shall be learning how to model basically metal nanoparticles and metal oxide nanoparticles. Quantum dot is beyond us for now. We have semiconductor nanoparticles. This is the where it's applied in electronics, where we build quantum dots. We will build quantum dots in bioimaging, in LEDs, in the solar panel, in NMRF. We build prototypes of electronic devices using a quantum dot. But most time, quantum dot will now need machine learning and deep learning algorithms for us to build an effective quantum dot. But we are going to model metal nanoparticles, and we're going to also model metal oxide nanoparticles. We have polymeric nanoparticles, where we have polymers from natural source, either synthetic or natural polymers. We build them to become nanoparticles like vaccine. We have nanovaccine, gene therapy, and others. We have carbon-based nanoparticles like nanotubes. This one is another high aspect of nanoparticle. As time goes on, you'll be able to learn how to model nanodots. We can call them nanodots or nanotubes. Like fullerene. Fullerenes is another aspect of advanced nanoparticle, graphene oxides, but these areas are not before us in this training. We have lipid-based nanoparticles and so on. So we are going to now look at, in the next session, how to use the principle that will guide us in building nanoparticle using computational tools. That is what we shall now look at in the next session. We shall not really focus on based on origin, because those ones are not really before us. So as we come over to the next session, we shall now look at what's the principle that will guide us in using ChemDraw to build this nanoparticle. All right, Mr. Austin, your hand is up.
Sorry, it's the one I raised before.
Okay, sorry. So we have 3 minutes to wind up. Prepare your questions. As we enter the next session, we shall now look at the principles of building nanoparticles. The ideas, how can I now build it? I have done justice to what these nanomaterials are, and I know I have done a good justice on that. We will now look at the principle that will guide me. How can I now model these nanomaterials and optimize them? So this is a course. We will not finish it today. It's a course. We'll continue. It's another course on its own. So we'll be taking it bit by bit until we master it. So thank you. If you have a reaction before we wind up, we can echo it. We have 2 minutes left, or better still, let's meet at the second session.